What specific problem does the mind evolution approach address within the realm of natural language planning, and how does it differ from existing methods in evolutionary search?
The mind evolution approach addresses the problem of optimizing natural language planning tasks, such as trip planning and meeting planning, by evolving solutions directly in natural language spaces rather than formal representations. This contrasts with existing methods in evolutionary search, like EvoAgent, which focus on evolving new LLM agents or require formal task definitions, necessitating significant effort and expert knowledge for each instance. Mind evolution employs a genetic search strategy that leverages the capabilities of a large language model, LLM, to generate and refine candidate solutions through a process called refinement through critical conversation, RCC. Additionally, it utilizes an island model to maintain diversity in the evolving population and integrates program-based evaluators to assess solution quality, providing textual feedback that enhances the refinement process. This combination allows mind evolution to achieve significantly higher success rates, such as over 95% on the travel planner benchmark, compared to the 7.2% success rate of EvoAgent.
How does the proposed mind evolution algorithm work? Illustrate it step by step, detailing the roles of genetic representation, fitness evaluation, and the refinement processes involved.
The mind evolution algorithm employs a genetic search strategy combined with a language model, LLM, to solve natural language planning tasks. It begins by initializing a population of candidate solutions through prompting the LLM, generating multiple solutions that form the first generation. Each candidate is then evaluated using a fitness function that scores the solutions based on optimization objectives, verifies constraints, and provides textual feedback. The refinement process involves a refinement through critical conversation, RCC, where a critic analyzes the candidate solutions and suggests improvements, which the author then incorporates into a revised solution. This iterative process of evaluation and refinement continues through selection, crossover, and mutation operations, ultimately evolving the population over generations until a valid solution is found or the maximum number of generations is reached.
Can you provide a concrete example of how mind evolution processes a natural language planning task, including details on candidate solutions generation, refinement, and evolution?
Mind evolution processes a natural language planning task through a structured approach that includes candidate solution generation, refinement, and evolution. Initially, it generates candidate solutions by prompting an LLM with a description of the problem and relevant instructions, resulting in n_text canvas times n_text seek initial solutions for the first generation. Each candidate undergoes refinement through a refinement through critical conversation, RCC process, where a critic analyzes the solution and provides feedback, which the author then uses to propose an improved solution. The evolutionary aspect involves using a genetic algorithm, where candidates are evaluated based on a fitness function that scores their quality and checks for constraint satisfaction. The best candidates are selected for reproduction through Boltzmann tournament selection, and new child solutions are created via crossover and mutation, incorporating feedback from the evaluation process to enhance the overall solution quality.
What are the specific advantages of using mind evolution compared to the baseline methods, particularly in terms of performance metrics on the trip planning and meeting planning tasks?
Mind evolution demonstrates significant advantages over baseline methods in both the trip planning and meeting planning tasks, particularly in terms of success rates. For the trip planning task, mind evolution achieved a success rate of 96.2% on the validation set and 94.1% on the test set, while the best baseline best of n only reached 77.2%. In the meeting planning task, mind evolution attained an 85.0% success rate on the validation set and 83.8% on the test set, with a two-stage approach using Gemini 1.5 Pro achieving even higher rates of 98.4% and 98.2% respectively. These results highlight the effectiveness of evolutionary search in leveraging critical feedback and iterative refinement which are not utilized by the baseline methods. Additionally, the empirical findings indicate that mind evolution's performance improves with the number of generations, showcasing its scalability and robustness compared to the more static approaches of the baselines.
How was the effectiveness of the mind evolution method validated in the experiments? Please describe the experimental design, the datasets used, and the metrics for measuring success rate and computational costs.
The effectiveness of the mind evolution method was validated through a series of experiments on 3 benchmark natural language planning tasks: trip planning, meeting planning, and the travel planner benchmark. Each task was split into validation and test sets, with trip planning having 320 validation and 1,280 test instances, meeting planning with 500 validation and 500 test instances, and travel planner evaluated similarly. Success rate was measured as the percentage of problem instances solved completely, with specific metrics like the success rate, also referred to as solve rate or final pass rate, reported for each task. Additionally, computational costs were assessed by tracking the number of LLM calls, input and output tokens, and the total API cost, providing insights into the cost-benefit trade-offs of the mind evolution approach compared to baseline strategies. The results demonstrated that mind evolution significantly outperformed baseline methods, achieving high success rates, such as 96.2% on trip planning validation and 85.0% on meeting planning validation, while also analyzing the scaling and contributions of various components through ablation studies.
What identified limitations or potential drawbacks does the author mention regarding the mind evolution approach, particularly in relation to its scalability and applicability to different problem domains?
The author identifies several limitations and potential drawbacks of the mind evolution approach. Firstly, while the method shows strong performance in natural language planning tasks, it relies heavily on the quality of the evaluation function, which can vary across different problem domains, potentially affecting its scalability. Additionally, the paper notes that the ability to check the correctness of a candidate solution does not guarantee the ability to generate a valid solution, indicating a gap in the approach's effectiveness. Furthermore, the author mentions that learned feedback models or self-evaluators can be noisy and unreliable, which may hinder performance in broader applications. Lastly, the paper suggests that the complexity of certain tasks, such as StegPoet, may pose challenges for the evolutionary search process, particularly as the constraints become more stringent.